OK，Good morning。在上课前，我可能还是稍微说明一下，就是关于这个防疫的这个关系，所以我们开始用这个线上小考的这个机制。那我请助教统计了前3次的这个线上小考的这个作业作答缴交这个情形。那我们把就是学生曾经补交或是未缴交的统计出来。那其实前3次小考大部分7到8成的同学还是都有准时在缴交期限以前完成上传这个作答缴交的动作。所以我们还是会持续用这样的方式，请同学作答完以后缴交这个作答过程。那我们就这个统计的资料，有针对几位同学，他可能因为作业小考作答未缴交或者是补交的这种情形，有点影响到他现在的这个期末的这个总平均。那助教会个别的去发信去通知有这样问题的同学。那如果大家不太清楚我现在说明的一些现象，其实可以去参考E3在昨天我们有公告一个关于小考的这个上传缴交的这个情形的说明。那麻烦同学还是希望在下一个礼拜一的小考能够有效去改善这个上传这个作答的这个缴交、迟交或者是补交这种现象。好，那我们就开始上课。So we just move to our final topic. As I mentioned before, right now our object is starts to moving, so our control volumes for the problems will be moved. So under these conditions, we have two topics. The first one is our object move with a constant velocity, and the second, our object is accelerating. Okay, so how to process these problems? So the first, we need to determine our reference frames because our object is moving. So if we would like to discuss the object move velocities, we need to determine the reference frame first. So as the figure showing here, if we fix the ground, this is our ground, and because the ground didn't move, so if we determine the reference frame fixed to the earth, so we call that is the inertial reference frames. And since we fix the reference frame at the ground, so we can tell you if our problem is a rocket, so we can tell you the rocket velocities relative to the ground. And we can also tell you the V-jet velocity here, and we can also describe the V-jet velocity relative to the ground. Okay, so and the sentence here, most problems are simpler if the frame is fixed to the moving object. So what are the meanings for this sentence? That means if our object moves with a constant velocity. So if our moving object moves with a constant velocity, so we can determine the reference frame as the moving object, and we still can call that is the inertial reference frame because the object is moving with a constant velocity. If our object is accelerating, and then we also push the reference frame on the object, and we will call that is non-inertial reference frames. Okay, so we go back to see the Reynolds transport series, and here the bottom equation showing here is momentum equations, and the left hand side is the sum of the force. We call that is the internal force. And the right hand side we have two items. The first item is the momentum change with the time in the control volumes, and the right hand side is the momentum exchange flow rate along the control surface. So, but I always emphasize there are two velocities. The first velocity is the fluid velocity relatively to an inertial reference frame, and the second velocity we call that is the fluid velocity relatively to control surface. So since we determine the reference frame already, and then we can try to describe the two fluid velocities relatively to different targets. The first is inertial reference frames, and the second is relatively to the control surface. So we show up an exercise and how to process the problem with the moving control volumes. So as you see here, this is the fluid jet, right? We have the one fluid jet, and there is a stationary nozzle produce a water jet with a speed of 50 meters per second. So we know that the B jet is with 50 meters per second, and the cross-sectional area of the 5 centimeters squared, and it is equal to 0.05 meters squared, and the fluid jet strikes a moving block. So the block here is on the movings, and is deflected 90 degrees relatively to the block. So deflected, and the direction is moving outward and relative to the block. And the block is sliding with a constant speed. So we have the V block with a constant, very important, with a constant speed of 25 meters per second on a surface with a friction effect. And we also know that the low densities of the water is 1000 kilogram per meter cubic. So please find the frictional force F acting on the block. Okay, so we have the frictional force acting on the block. So we start from the force diagram and the momentum diagram, each others. And so for the force diagrams, we first discuss with the force along the x directions because our target is the frictional force here. And the right hand side, we also make a balance of the momentum flow along the x directions. Okay, so we actually know that we have the force along the x directions is the frictional force only, and then the frictional force will be equal to the momentum in and the momentum out. So along the x directions, and we take a look for x directions, we only have the flow in, and the flow out is only the upward directions. There is no any momentum flow along the x directions. Why? The out is directly upward because we fix the reference frame for this problem on the block. Here, why we fix the reference frame on the block? Because the block is moving with a constant velocities. So if we fix the reference frame to the block, and then the outflow directions relative to the block has only the velocity upwards. There is no horizontal velocity. So for this problem, since we already fixed it, the reference frame to the block, so we only need to consider the momentum flow for the inflow directions. We don't have any outflow contribute to the x directions momentum flow. Okay, so because we only have the inflow momentums, so this is the minus m rate multiply the v1 velocities. Okay, so the first, based on these equations, the first we didn't know the m rate, right? And we also didn't know the v1 velocity. So how can we calculate the m rate? As we know, the mass flow rate is equal to the low density and the cross-section area, and if we know the velocity, right? And because the velocity here is, we need to find out the velocity relatively to the control surface. So we depict the control surface with the block boundaries, and since we know the Vjet, the Vjet is 50 meters per second, and the block moves with a constant speed of 25 meters per second. So we know that the control surface will move to the left with a constant velocity 25 meters per second, and we have the V-jet is 50. So the velocity here, we know that we can is equal to the V-jet minus the V-rock, because we need to have the relatively velocity to the moving block. Okay, so what's the raw density? We know this is 1,000 kilograms per meter cubic. And what is the cross-section area? Here is 0.05, and we have the V-jet is 50 meter per second minus the 25 meter per second. Okay, and we use the calculator to compute the answers. So the 50 minus 25 multiply the 0.05 and multiply 1,000 density. So the mass rate is equal to 1,250 kilograms per second. And what is the V1 velocity for the inflow side? Okay, since we the V1 velocity should be the fluid velocity relatively to the reference frame. Okay, and we pick out the reference frame on the block right here. So the V1 velocity relative to the reference frame is also equal to the V-jet minus the V-block. Okay, so it is also equal to 50 minus the 25 is equal to the 25 meter per second. So we have equation 2, and this is our equation 3. We just put on the 2 and the 3 into the equation 1. Okay, so I rewrite the equation 1 is the frictional force equal to the m rate multiplied by V1, and we have the m rate is 1,250 multiplied 25, and this is the equal to, it is the equal to the 3,125 3,1,250, and this is our frictional force. This is our frictional force. Okay, so we have a frictional force is around 3,1,250 newtons. Okay, so for this problem, we actually fix the reference frame on the moving block. But the idea is because our moving block move with constant velocities, so that's why we can use the because we fix the reference frame on the block, so we can solve this problem very easy to follow this the equations shown here. Okay, so we check that the answers a little bit different. That we here's okay, it is not equal to 0.05 meters square. So the area is 5 and 10 minus 4 powers meters square. And we rewrite we multiply the answer here is the 5 and the 10 minus 4. So this is equal to the 12.5. Okay, so here is the 12.5. Okay, so there is 312.5 newtons. Okay, sorry for that. So this is the final answers is the same the answers I show in here. Okay, but the questions here, if we don't use the reference frame on the block. Right now we change to the reference frame we fix to the ground. So how different for our problems? So as you see, because we fix the reference frame on the ground, so the velocity of the outflow is not directly upward. This is for these directions. Because we don't use the reference frame to the block. So what's the problem? Again, for the x directions, right now we have the outflow rate and we still have the inflow rate. But for the force items, we only have the frictional force also. But the right hand side is different. But first, we consider the outflow momentum. So this is the n rate B2 and we project to the x directions, so multiply the cosine theta. And there is still the inflow momentums, so minus the m rate and the v1. So we know that the frictional force is equal to the m rate v1 minus the m rate v2 cosine theta. Okay, so the first, what is the m rate? So as we mentioned before, m rate is equal to rho a, right? And the velocities. And again, the velocity is still the fluid velocity relatively to the control surface. So since we fix the reference frame in here, and we know that the block moves to the right with a constant speed 25, and the fluid jet is with the 50 meter per second velocities. So for the mass flow rate is the same, is equal to a rho a b jet minus the b block. This is the same. And what is the V1? The V1 is the fluid velocity relatively to the reference frame to the ground. So the V1 is still the V equal to the V jet. And what is the V2? The V2, because based on the continuity equations, we know that the V1 is still equal to the V2. So this is also the V jet. but the V2 cosine theta. What is the V2 cosine theta? Because the V2 project cosine theta is equal to the velocity along the x directions. And since we know that the block is moving with a constant speed to the right, so the V2 cosine theta is still equal to the V block. So then we can rewrite the equations here because we know that the m rate, this is the m rate multiply the V1 minus the V2 cosine theta. And the m rate is the rho A V jet minus V block. This is the m rate. And we inside here we know that multiply V1 is the V jet and the V2 cosine theta is equal to V block. So we know that the frictional force finally is equal to rho A V jet minus V block squared. So this is the same, even though we change the reference frame to the ground, but the final answer is also the same. So you can go back to compare to the previous. We fix the reference frame on the block, and there is a V jet minus V block for the mass rate. And then we also have the V1 is also the V jet minus V block here. So I would like to emphasize that even though you change the different reference frame, but the final answers didn't change since you determine the different reference frames. But for this problem, because the object is moving with constant velocities, so that is more convenient if you can fix the reference frame to the moving object. Will be better to process these problems, because for this problem we fix the reference frame to the block, so there's no any outflow contribute to the x directions. We only need to consider the momentum for the inflow part. Okay, so but now our problem changed to the object is accelerating. So we don't fix the reference frame to the rocket problems. So in that way, we will fix the reference frame on the ground. And right now, our problem, the rocket is moving upward with the speed vr. We know that is the rocket velocities, and respect to the ground, because we fix the reference frame on the ground. And there is the exhaust gas with the velocity VE, but it is downward respect to the rocket. Okay, this is the condition for our problems. So we first draw the force diagrams. So for this problem, we need to consider the jack force and the downward, and we have the weight of the total systems, and we have exhaust gas pressures, and with exhaust gas cross-section area PEAE. So, and the right hand side we have the momentum flow balance. So as we know that for the rocket problems, the mass inside the rocket will decay because the gas will exhaust outside and to contribute the pressures to push the rocket upward. And we only have the one momentum outflow and rate V0 here. Okay, so if we write down the equations here, the left hand side is the force balance, the PEAE is upward directions minus the total weight and minus the drag force. And right hand side we have the momentum changes with the time in control volumes, and there is only have the one outflow momentum rate. Okay, so the idea is we have the outflow momentum and rate v zeros. Okay, so we only know that we have the exhaust gas velocities and with the downward, and we know that the rocket is upward with the flow velocity. Upward velocity is Vr because we fix the reference point on the ground. And we know that the Vr is the relatively to the ground, and the Ve is the velocity relative to the Vr rocket. So the flow velocity on the outside V0 should be equal to the Ve minus the Vr. So we rewrite the momentum outflow to Ve minus Vr. Okay, so we can summarize the final equations based on the momentum equations. So again, I described it. We have the pressure contribute to from the exhaust gas, and we need to minus the total weight and also minus the drag force, and is equal to the momentum change with the time in the control volumes here, and we have the momentum outflow. But why we use the minus? Because the force contribute to from the momentum flow is downward, so there is the minus. Okay, so we try to expand our equations. So we have the PEAE and then minus the total weight minus the drag force is equal to, we have the partial differential, so is equal to the VR dmr dp, and we can fix the mr, and there is a dvr dt, and the right hand side is the minus m rate ve is exhaust gas velocity, and the plus the m rate vr. And also this is equal to, we just put the VR together, so we have the VR, and the inside we have a dmr dt, And then there is also the VR, so this is plus the M rate. Okay, we just push the two items together and take the VR outside. And we still have the M R D VR dt minus the M rate is source velocity VE. So if you focus here, these items, what is the dmr dt plus the m rate? This is the equation similar to our continuity equations here. And based on the continuity equation, we know that the total mass change with the time in the volume plus the mass flow rate will be equal to 0 because this is satisfy the mass conservation. Okay, so we have the continuity equations. We know that sum of the total item here is equal to 0. So we can rewrite the equation. We don't have these items because this is satisfy the continuity equations. So for above equation, we only have the PEAE minus W minus the jet force is equal to the MR dVR dt minus the M rate VE. And we move the M rate VE to the left hand side. So there is a PAE plus the M rate VE minus W minus D, and then we only have a M rocket mass dVR dt. Okay, and usually we call that the PEAE plus the M rate VE is the thrust force. Because this is the force support to push the rocket move upward. So we call that is the thrust forces. Okay, so we still can rewrite the equation to the T is the thrust force minus the weight minus the drag force is equal to the NR rocket mass dVR rocket velocity dt. This is the equations usually is applied to analyze the rocket performance and predict the rocket moving. Okay, so this is a very important equations. It just derived based on the continuity equation and the momentum equations. So let's keep going. Right now, we ignore the drag and the weight, so the equation can reduce to the T is thrust force equal to the rocket mass and the dVR dt. And we assume the instantaneous mass of a rocket is given by the mr is equal to the initial mass minus the mass rate multiply the timing. Okay, so you can put these assumptions, go back to the equation here. So we know that the T is equal to the initial mass minus the m rate T, and we have the dVR dt here, And we just reorganize the equation is mi minus m rate t, okay, and this is over, sorry, I push downward, the mi minus m rate t, the t here, and the left hand side is the t over 1 dvr, right? And we can do the integrations because we know that t is start from t time is 0 to the t finals, and there is still the mi minus the m rate t over dt, and the right hand side is the thrust force over 1, but we do the integration, we still start from the velocity is 0 to the final velocity and the dvr. Okay, so we do the integrations for the time. So this is equal to the rho mi minus the m rate t divided the m minus m rate, and the integration interval is start from t to tf, and the right hand side here is equal to the tdf. Okay, so we just push the number inside, and we know that this is minus n rate over 1, and the inside is the long mi minus n rate. Right now the t is tf minus, we put the 0 inside, so this is the long initial mass, and this is equal to the Vf divided T. Okay, and we just take the Vf, keep the Vf is the final rocket velocity on the left hand side. So we move the T to here, so it's the minus m rate over T, and we assume the mi minus MITF is the final rocket mass. Okay, so we let the mi minus the n rate multiply the tf is the final mass. Okay, so the inside is the rho final mass minus the rho initial mass, and we'll put the minus inside, so we can rewrite to the equation is equal to the initial mass rho minus the rho final mass, and because of the minus, so it's equal to the rho mi divided m final. Okay, so we just summarize the final equation. The final rocket velocity is equal to thrust force divided the mass rate. multiply the known MI divided NF ratios. So based on this equation, we know that the rocket velocity will increase when the thrust force increase. And we know that the ratios between the initial mass and the final mass, if the ratio of the mass is increased, the rocket velocity also increase. So this is very important to try to, based on this equation, we can predict the burnout velocities. Okay, so for this equation, it is very important. Please keep in mind and try to prove the formula shown here by yourself. So again, we start from the momentum equations. We start from the momentum equations and write down the force balance is equal to the momentum balance. And the momentum balance for this problem, we have additional contributions from the momentum change in the control volumes. And then we have a momentum outflow. And we apply the continuity equations. Okay, we apply the continuity equation. So we ignore some items. And then we just summarize the final equation like this formula shown here. And the next problems, we just ignore the drag force and the total weight. So we can simplify the equations. Is equal to the thrust force equal to the rocket mass dV dt. And the instantaneous mass of the rocket is given by these equations. And then we process the integration problems, and then we have the final formula shown here. Okay, this is very important, and the normal we apply to the momentum equations to the rocket behavior. And because these problems, our object rocket is accelerating, so we need to fix the reference frames on the ground. We cannot fix the reference frame on the rocket because the rocket is accelerating. The rocket didn't move with a constant velocity. Okay, so our final topic here is the angular momentum equations. So this is very useful equations can process the problem related to the pump, turbines, and the fans, and something like that. So we may have a 10 minutes break. After the break, we go back to the class and I will teach you more details about the angular momentum equations. Okay, so right now it's time for break.